Subject of this video will cover how the slope of a tangent relates to local linearity. In order to make this a little easier to understand, I want to think about this like a projectile. So just as an example, let's say that you're 6 feet tall and you throw a baseball straight up in the air at 50 feet per second. You may have learned a little bit about how to build what's called a projectile model. So the 6 would represent the initial height, the 50 the initial velocity, and then just think of this like the gravity part that's bringing it back down. Let's graph this and then connect the two of them together. Okay, here's what the graph looks like, and specifically this is the equation. Just entered it in here, and we should know from the degree of this polynomial being 2 that it has to be parabolic, 6 being the y-intercept. Now, what I'd like to do is we're going to choose a point on this graph. I can randomly choose it wherever I want to. And let's going to take a look right here, maybe when the ball is coming back down. Note the independent variable is measured in time in seconds, and the dependent axis is height in feet. Now, specifically, what we want to do is look at what happens when that ball is coming back down in terms of its rate of change of height with respect to time. There's a special word for that, change in height or change in distance with respect to time, and that's something that you would cover in a physics class. We're going to call that instantaneous velocity. So again, think of instantaneous velocity as just the velocity or speed at a specific moment in time, and then what we can do is measure that by finding the slope of the tangent, because the tangent is measuring change in distance with respect to change in time, and that's what instantaneous velocity would measure. So we need a tangent, so I'm going to choose this point and just draw in a tangent line. You can see it there in blue, and then we can see what its slope is by looking at this box here. Its equation is given by this y equals equation, and its slope is about negative 33.2. So which means at this point in time, specifically at x is equal to 2.6 seconds, the ball is falling down towards the ground at a velocity of negative 33.2 feet per second. I hope you're considering the question, how can this blue straight line approximate the slope of this red curve? As a curve approximating being approximated by something that's straight doesn't quite make sense. So there's something I'd like to show you here. We're going to take a moment to zoom in on this particular area a little bit. Now notice it's a curve, it's a parabola. If I zoom in towards that point, there is a little bit of a gap between the tangent line and the actual curve itself. But as you can see, there's not a lot of difference between them right there. And if I do this one more time, I'm going even closer than I did before, they're almost indistinguishable. So if I repeatedly do this, you can see that actually that slope of that tangent is going to be exactly the same as the slope of the curve. So taking that idea to the next logical conclusion, I could pick any point on this graph, and then if I zoomed in and I zoomed in and I zoomed in, that curve will appear to be straight. So anywhere that you draw a tangent line and then zoom in and zoom in and zoom in, not only does the curve become straight, but it also becomes imperceptible from the curve to the tangent itself. And there's the name of that property is called local linearity. And local linearity is basically going to guarantee this statement. The slope of the tangent line is interchangeable with the slope of the curve. So why would you actually want to find the slope of the tangent? It lets you know through having to estimate. We're not going to be having to ask you estimate the slope of the curve right here. We're going to have a tangent line to do it. So as long as you understand, to summarize this, that the slope of this blue line called the tangent is the same as the slope of the curve at the point of tangency, you've got it.